factor the denominator. Figure out how to factor the denominator if it's not already factored. I gave you these already factored. Well, almost already factored. Once you figure out how they factor, if you have a simple linear factor, put an A over it, a letter over it. What happens here? This is, what do we call this in college algebra? So if I wrote out the polynomial, p of x is x squared times x plus 1, what are the roots of that polynomial? What makes that polynomial 0?
Outside of that.
What numbers make that polynomial 0? -1 and 0. And 0 is what we call a root of multiplicity 2. It's a root of multiplicity 2. It's a root that appears twice. Because if you wrote it out, it's like x times x plus 1, right? So -1, 0, and 0. So it's a root of multiplicity 2, they call it. It appears twice in there. So when you see roots of multiplicity 2, you're going to have to put them once by themselves and once with the higher power. So if this was an x cubed, you'd have an a over x plus a b over x squared plus a c over x cubed. And then, see, this is a root all by itself, so it goes there. So how do I decide what to do down here? Well, what's this? X equals 1 is a root of multiplicity 2, so it appears twice. A over x minus 1, b over x minus 1 squared. This, what are the roots of x squared plus 4? What makes that equal to 0? And 2 squared plus 2 is 4 plus 4 is 4 plus 4, 8, not 0, right? You can't get 0 unless you use complex numbers. Plus or minus 2i are the roots there. So it doesn't have any real roots. So since it doesn't have any real roots, we can't factor it into 2 linear factors. Since you can't factor it into linear factors, you can't break it into pieces like we did this one. Therefore, the top gets more complicated. You do a linear factor on top.
So if we had x squared plus 4 by itself on the bottom, there are no other problems, we do a linear factor.
Right.
Or, okay.
Yep, that's right. So if you had 3 over x squared plus 4, you'd write it as ax plus b over x squared plus 4. But if you had this,
You wouldn't need to.
you wouldn't need to because you don't need partial fractions,
Right.
because this is a nasty inverse tangent problem.